Okay, guys, can you guys hear me? Hey, guys, can you guys hear me? Yeah, you can actually use the group chat to talk with me. Yes, on the top right corner of your control console, there is actually a chat. You can basically do the communication with me using the chat, right? It's our new session, new lectures. We might have some students, some new students trying to figure out how to do the login. So let's try to give it like 1 more minute while we're receiving more students. All right? Yeah, we always have some new students for the new session. Maybe they're trying to figure out how to do the login. Let's try to give it 1 more minute while we're receiving more students. Okay. All right. I think we can get started. Hi guys. Welcome to our math competition lecture courses. And we just finished up our AMC 12 bootcamp, right? So basically, we have some students went to our AMC 10, AMC 10, and AMC 12 related bootcamp. We actually have some introduction about most of the important concepts for the AMC 12, 10 related lectures. And that was actually a bootcamp. So basically, we focus more on give you a very quick overview what are needed, what are not needed, so on and so forth for the AMC. Now we actually go to our knowledge-based lecture. A knowledge-based lecture is actually a more detailed, in-depth explanation rather than our bootcamp, because we have like an entire session talking about one or two concepts for the AMC math competition, and same thing for like the Canadian math competition as well. So we have like more problems, more time, we can do the interaction, so on and so forth. And this is actually our knowledge-based lecture. All right. Our knowledge-based lecture actually organized by different sessions. We have 8 sessions in total. Today is going to be our first session, session 1, and we're going to talk about sequence and proving strategies in the discrete math. So this is our session number 1, sequence and the proving strategies in discrete math. Okay, so before we get started, I'd like to give you guys a quick overview about pretty much like the syllabus, what we will be covering in this current session. Okay, so this is actually a quick overview about most of the important parts we're going to be talking about in our current session. We're going to start our session talking about one of the most important strategy in our discrete math. Try to do the proving. That is the mathematical induction method. We're going to go to more details talking about the specific method. This method is very useful whenever you're dealing with some relatively difficult problems. You have to do some proof and try to prove some natural number related concepts. And then we're going to talk to another topic, which is what we call the minimum principle and proof by infinite descent. This is also 2 very important strategy. You won't be able to see that in the very low level math competition, but as long as you go to relatively higher level, you will be able to have more and more exposure to these 2 technologies. And then we're going to go to the discussion more on the pretty much like the sequence. We're going to talk about the general formula of a sequence, the recurrence formula of a sequence. These are 2 very important methodologies when you're trying to evaluate a sequence, right? And then moving forward, you want to see how we can determine the sum of a given sequence. You know, in our question AMC or Canadian exam, from time to time, you would be able to see something like, I give you a sequence with either recurrence formula or general formula. I need you to determine the first n-term sum, right? This is actually a very important way we like to do this kind of analysis. And we're going to be doing exactly the same thing for our current lecture. And then moving forward, we're going to be talking about two very important sequences. They're actually the twin brothers, right? Arithmetic and geometric. Instead of giving something very basic, we like to introduce some flowery problems, how you can use the property from the arithmetic and geometric, try to solve the problem. And then we're going to talk something what we call the high order arithmetic sequence. You know, we're kind of like familiar with the basic arithmetic, but moving forward, we like to introduce a higher order arithmetic sequence. There are some interesting properties based on this kind of sequence. And in some high-level math competitions, you might be able to see some applications. We're going to specifically introduce the eigenvalue method and eigenvector method. Try to use the recurrence formula, try to determine the general formula of a given sequence. And we're going to introduce the fixed point method. This is also a very important method. You're going to use it a lot in most of the sequence and, you know, like the function, this kind of related applications and proving strategies. And last but not least, we're going to be talking about the Fibonacci sequence. We know, like Fibonacci by definition, right? From the third term, the value of the term is always the sum of the previous two terms. But actually, there are a lot of interesting properties from the Fibonacci sequence. All the way go to the high-level math computation, you will be able to see a lot of applications using the Fibonacci sequence. So basically, this is kind of like a big overview, what we will be talking about in our current session. Okay, just give you guys a rough idea what we'll be looking at. Okay, if everything is good, let's go to our first lecture. Let's go to our lecture number 1. The lecture number 1 is the mathematical induction method. Okay, mathematical induction method. This is a very important proving strategy for most of the sequence-related problems. But before we jump to the mathematical induction method, let's try to do a very quick overview about a sequence, right? Because this lecture, we're going to talk about our sequence AN. So let's try to have a quick overview. What is a sequence talking about? So basically, the definition of a sequence is very understandable. It basically means numbers in a certain order. Right? This is the definition of a sequence, numbers in a certain order. So whenever we're talking about a certain order, trust me, this is actually a very kind of like very loose concept. So what is like a certain order, right? So this certain order can be something very accurate. Let's say I want to have an arithmetic sequence. I want to have a geometric sequence. These are two sequences, right? It's very accurate. You need to follow a specific pattern, right? As long as you're not follow this specific pattern, this is not an arithmetic or geometric, right? That's a sequence. Or this can be very wide, certain, very wide order. For instance, we can say I have an increasing sequence, or I have a decreasing sequence, right? As long as the numbers are going bigger and bigger, this is increasing, or vice versa, this is actually a decreasing sequence. So, you know, in this time, like the standard is very loose, right? The first one is very accurate, very tight, while the second one is kind of like flexible. Or we can have no pattern. Let's say I want to have a random number sequence, right? I might have a sequence. So this sequence, every single number is actually a random number. So this is also a sequence, right? No pattern is also considered to be a certain pattern, aka no pattern, right? Or I have maybe the same, all the numbers are the same elements, right? They're all considered to be certain order. So that being said, as long as you're trying to define a sequence, there's not a very strict, you know, It's kind of like a black and white line, right? As long as you have a certain order, you can define your order and you can present listing out all the numbers based on your order. This is actually a sequence. You don't really have to go too much about the specific order. Very general, very tight, or even no pattern, no nothing, no problem. So these are all considered to be a sequence. I think this is pretty much a concept. Everyone already knows that, right? And before moving forward, another very important part I like to have a quick discussion is that we want to do a quick comparison between a sequence and a set. You see, when we were in our function-related session, we talked so much about set. Now it's the sequence. We like to do a kind of comparison between these two parts. So what are the most important difference between a sequence and a set? So long story short, in sequence, order matters. Right? Let's say 1, 2, 3. If this is a sequence, 3, 2, 1. This is another sequence. Right? One is increasing sequence, one is decreasing sequence. Well, from the set perspective, order does not matter. Right? This is quite understandable. So 1, 2, 3, 3, 2, 1, they're basically talking about the same set, right? Because order is not so important. So here you can have a quick observation. We're always using the same denotation, this curly bracket, right? For sequence or for the set, but basically they have like two different underlying explanations, right? One, in one circumstances, sequence, order matters, while for the set, the order doesn't matter. Well, there's another very important part, important concept between the sequence and the set, is that can I have the duplicate element? Of course, in sequence, you can have the duplicate elements, right? You might have a constant sequence, 1, 1, 1, right? Every single item in the sequence is number 1. Of course, these are infinitely many duplicate items. It doesn't matter. However, we all know that in set, you can't have any duplicate items, right? Every single item must be unique. That's the basic definition from a set, right? So that being said, you will be able to see there are some similarities between the sequence and set, aka they're using the same denotation. However, the key points, there are two very important points which help you guys to differentiate the sequence and the set. So in any circumstances, you won't be able to kind of like miss these two concepts, right? I think this is something quite understandable. All right, as long as we're done for this kind of like a basic introduction about a sequence, I think it's time for us to talk about this mathematical induction method. So mathematical induction method, this is actually a very important tool, a tool for integer related proof. A tool for integer related proof. What is that? You know what? Talking about a proof in mathematics, this is always something very challenging, right? I think most of the mathematicians, they hate proof. You know, proving a problem is always the most complicated part in mathematics. You know, long time ago, you know, we're talking about like thousands of years ago, when mathematics was first time introduced, there's so many problems, so many things needs to be proved. Even though for today, there are still a lot of like a world-class complicated problem for us to prove it, right? So talking about all the proofs in mathematics, generally speaking, you're talking about two parts. One is the geometry-related problems. One is the algebra-related problems. Okay, these are the two major problems in this entire math. Okay, but you know what? All the way to today, you know what? This is like 2022. All the way to today, the geometry-related problems, there's not so many leftovers. Most of them has already been solved. You know what? Why? Because we have already created the coordinate geometry. Coordinate geometry. So previously in the ancient Greek, right? So people has to figure out a lot of complicated theorems, try to solve some weird problems, so on and so forth. You really need a lot of kind of like inspiration. You need a lot of intelligence in order to fix all those problems. However, as long as we figure out the coordinate geometry, a complicated geometry problem can always be reverted or converted into an algebra problem. We can use the algebra calculation to try to help us solve the geometry problem, right? So in our bootcamp lecture, we already spent a lot of time talking about how to convert all the geometry-related angle problem, area problem, or the segment length problem into the calculation in algebra. So that being said, at this moment, there are not too many leftover geometry problems that yet to be proved. Of course, there are some. For instance, I can give you some example. One is actually what we call squaring the circle. Whenever I have a circle, how can I create another square and make sure the square has the same area of the circle? You know what? This problem is not difficult, but the most problem is that in the square, you have to figure out how you can arrange this pi, right? Because in the circle area of pi r square, this kind of pi is actually an irrational number. So people doesn't know how to really convert it into a square. But this is actually one world-class problem to be solved. The other one is what we call the angle trisection. As long as I give you angle, how can I basically trisection, process the trisection, not the bisector, but trisector. Make sure this guy, this guy, this guy, they all have the same measurement. So this is also another big problem for us to solve. We really have no idea how to, using the compass, using the ruler, how to solve this problem. So these are just basically to name a few, right? There are some, leftovers, for the geometry part, but generally speaking, most of the geometry problem has been solved using the coordinate geometry. Well, the other big part is going to be the proof in algebra, especially in the number theory related part. Okay. For the famous Goldbach conjecture, for the famous Fermat last principle, these are all algebra problems. They're basically focused on the number theory, and there are countless number theory related problems yet to be solved. And this is actually the focus of our current mathematics. Most of the mathematicians are trying to give a proof for all those leftover algebra problems. So that being said means having more understanding the proving strategies for the algebra problem is actually one of the hot topic in our entire math. A lot of mathematicians trying to find out a very fancy or complicated way to try to prove the algebra related problem. Okay? And today, the mathematical induction method is actually indeed a very powerful way for us to solve some algebra related problem. And that's the rationale why we like to start our lecture talking about the mathematical induction method. So what are the mathematical induction methods applications? Right? Why we want to have such a method and how this method is actually introduced help us to solve the problem. This is going to be the major focus of our today's lecture. So what are the problems we need to solve? So basically, we always see some kind of problems like this. A property, Pn, for instance, you want to prove such a property holds for natural numbers. Natural number is 1, 2, 3, all the way to whatever, right? So from time to time, you might be able to see a property which is hold for the natural numbers. For instance, one of the most important thing, 1 plus 2 plus 3 all the way to n, right? That one equals to n plus 1 divided by 2, right? This is actually something quite understandable, right? This is actually a method. This is actually like a conclusion reach hold for all the natural numbers. Something 1 square, 2 square, all the way n square equals to 1 over 6 n plus 1, 2n plus 1, right? So these are kind of like a conclusion or property hold for all the natural number, okay? And how to prove such a problem, right? Mathematical induction method is actually a methodology which would help you to solve all these kind of problems. So that being said, why and what is mathematical induction method? Mathematical induction method. So for short, we call it MIM. So what is that? So mathematical method actually give you a template how to solve such a problem. Okay, as long as you follow the template, any kind of this positive integer or this natural number related problem could be solved just using such a template. So what this kind of template looks like? So we basically need to solve the problem for 3 steps. Step 1, if we can validate when n equals to 1, the property holds. Okay, validate as long as n equals to 1, the property holds, which is quite understandable. You just plug in the value n equals to 1 on the left, on the right, you're good to go. And then step number 2, you can hypothesize when n equals to k, this property holds. Here, very important. I'm not asking you to prove whenever n equals to k, this property holds. I just want to do a hypothesis. Suppose or hypothesize whenever n equals to k, the property holds. You do not have to provide any explanation, any proof. You can just suppose that one holds. Okay? Well, the most important thing is, as long as you make such a hypothesis, you need to prove out whenever n equals to k plus 1, the property also holds. Well, this is the most important thing. In step number 2, you're going to do 2 things. First thing, you have to hypothesize, which is guess, suppose, whatever, whenever n equals to k, the property holds. You don't have to prove anything. You can just take it for granted. However, using such a hypothesis, you have to prove out whenever n equals to k plus 1, the property also holds. So this is the part you need to process the proof. So here, no proof. Do you need a proof? No proof. But here, do you need a proof? You definitely need a proof. Okay? So step number 2 is 2 steps. Hypothesize whenever n equals to k, the property holds. And using that kind of hypothesis, you want to prove out whenever n equals to k plus 1, the property also holds. As long as you can finish up the first 2 steps, whenever you go to step number 3, you can claim the property holds for all the natural numbers. Okay? So these are the 3 steps. So this is actually how the mathematical induction method works. Step number 1, you want to validate whenever n equals to 1, the property holds. That one is fairly understandable. You plug in the Lagwell, you just plug in the number, you're good to go. Well, step number 2 is you want to hypothesize. Whenever n equals to k, this property holds without any proof, but taking from that hypothesis, you want to prove out whenever n equals to k plus 1, the property also holds. Okay? with these two steps, step number 3, you can actually come up with a conclusion. Voila, okay? This property holds for all the natural numbers. So this is actually the mathematical induction method. So people is going to ask, hey, Alex, why you follow this like 3 steps? You can make sure the property is going to hold for all the numbers. I'm going to give you some explanation. Why? This method works for all those properties. So step number 1, you just find out whenever n equals to 1, the property hold. So this is actually considered to be step 1, a base case. You want to find out the minimum number n equals to k, n equals to 1 to make sure this property holds. Well, the most important thing is step 2. Whenever you suppose n equals to k, it works. You want to prove n equals to k plus 1, it works. This is actually generate an internal iteration. So for instance, because k is actually any kind of number, right? Whenever k equals to 1, it means that this is the base case you just introduced here, right? K equals to 1 is whatever you check for your base case number 1. Of course, k equals to 1, it should work. You already prove it in step number 1. As long as you know k equals to 1, it works. This is going to help you to prove n equals to k plus 2, k plus 1 actually equals to 2. The system works, right? Whenever k equals to 2, you can use n equals to 2 to prove n equals to 3, it works. Whenever k equals to 3, it works. You're going to go to 4, it works. So this is going to be an iteration, one after another, right? So that being said, it's more like a domino effect. As long as you can do 1, k works, k plus 1 works. K works, k plus 1 works. K works, k plus 1 works. So that being said, you would be able to iterate all the numbers because k can go to whatever, right? So your k plus 1 can also go up to whatever. So that being said, this kind of internal logic is going to help you to prove all the numbers, 1, 2, 2, 3, 3, 4, 4, 5, so on and so forth. And you would be able to cover all the numbers based on such an assumption, right? So your step number 3 is going to be a conclusion. It works for all the positive integers, right? So this is basically a very understandable process why you have this internal iteration for these 3 steps. So that being said, in order to use our mathematical induction method, these 3 steps, all of them are equally important. You can't miss any of them. For instance, step number 1. Step number 1 is considered to be the base case, the foundation scenario. You need to have something to start with, right? Let's say if you prove n equals to 1, and then during your iteration process, you're always going to start with n equals to 1, and then go to 2, 3, 4, 5, whatever. However, if you can't even prove n equals to 1, it works, means the foundation part doesn't work, then you won't be able to start your iteration, right? Here, you really need the foundation case. However, if you do not really get a chance to prove the foundation case, how can you start, right? If you want to do if you want to create like a skyscraper, right? You need to have the good foundation. Your floor number 1, your foundation is the most important. So that being said, the first step, even though it's easy, you just plug a value. This is very important because that's the very start of this entire iteration. This is very important. Okay? All right. As long as we're done for the first one, the second part is also very important because this is like the core business. You need to set up this internal iteration from whenever k go to whenever k plus 1, because k and k plus 1, they are adjacent two numbers and they are keep changing. As long as k iterates from 1, 2, 3, 4 up to whatever, so your k plus 1 also iterates with anything. So that being said, this kind of seamless proof from k to k plus 1 create this harmonic internal iteration and help you to prove every single step, every single integer, to make sure this property holds for everything. There's no skip, there's no gap. It works for 1, 2, 3, all the way to whatever. There's no gap in between. And as long as you have such a thing, number 1, number 2, there's 2 steps as a foundation, you can basically come up as a conclusion. Okay, with everything, your mathematical induction method works and it covers every single positive integer. Okay, this is actually the entire thinking process, why we want to have this mathematical induction method and how this method could work. Why this could work? Because it has this harmonic internal iteration. Okay, so one of the most challenging thing is, I think, how you can do this proof, right? From n equals to k to n equals to k plus 1. It actually kind of like this is like the core business to this, right? You need to use the hypothesis you did for n equals to k, try to prove n equals to k plus 1. This is actually the most important thing. And most of the flowery things happens in such a proving process. I'm going to be giving you guys different scenarios, different problems, and you will be able to see how we can utilize this in our proving process. All right. I think that's pretty much. I think the logic is very understandable, right? Like the foundation process is very understandable. You know how this works. 3 steps, and you'll be able to utilize this mathematical induction method, try to prove some problems. Okay. You know what? Let's go for some real problems. This is very like theoretical, right? Abstract theoretical. Let's try to use some real problems. I'm going to be showing you guys how you can make the magic here. How you can find out from n to n equals to k to n equals to k plus 1. All right. So let's get started to some sample questions. The first one is, let's go for warm up, a very easy problem. Question number 1. Please prove for any natural number n, 1 cube plus 2 cube, 3 cube, all the way n cube equals to n plus n times n plus 1 divided by 2 perfect square. This is actually a very easy peasy conclusion, right? Everyone knows that we should know the perfect square sum of all the natural numbers and also the perfect cubic sum, right? For all the natural numbers. Okay, let's try to use this problem. Let's try to use this problem as an example, and I will be showing you guys how to use the mathematical induction method to try to solve the problem. So, proof. Let's go for this 3 steps, right? Step number 1, I need to find out a base case. Base case is basically n equals to 1, right? Whenever n equals to 1, left equals to 1, right? Right is also equal to 1. Just plug in the value, right? 1 times 2 divided by 2 perfect square equals to 1. Voila, it works for n equals to 1. Then step number 2, like I said, you want to suppose when n equals to k, the property holds. In the future, I'm just going to write pH. Okay, the property holds. AKA what? 1 cubic, 2 cubic, k cubic, k plus 1 divided by 2, perfect square, right? This part you do not have to give any proof. You just hypothesize. That's work. And then we're going to check whenever n equals to k plus 1, how the number works, right? So whenever k equals to n equals to k plus 1, the left-hand side is going to be n cube, 1 square cube, 2 cube, k cube plus k plus 1 cube, right? You just basically write that. And like I said, the most important thing is you need to use your hypothesis in order to process your n equals to k plus 1 related proof, which is quite understandable. We just already have our hypothesis here, right? We already have our hypothesis here. We're just going to plug in here. So this guy is going to go to k plus 1, 2, perfect square, k plus 1, perfect cube. Right? Quite understandable, right? Nothing too complicated. So, following part, you see some common factors here, right? This is going to be a common factor between just two terms. So why don't you just plug it, drag them out? This is going to be a perfect square. This is going to be what? 1 over 4 k square, k plus 1, right? K plus 1 perfect square, 4 k square plus 4k plus 4, right? K plus 1 perfect square. And then the other one will be k plus 1 perfect square plus 1 perfect square. K plus 1 perfect square, right? So that one is going to be k plus 1, k plus 1 plus 1. Perfect square divided by 2. Is it right? You see? I just do some quick factorization. I get this. And this is exactly, you see? Whenever n equals to k plus 1, the right-hand side is going to go to what? K plus 1, k plus 1 plus 1, 2, perfect square, right? This is exactly what you need to prove, right? I have to make sure as long as I replace n equals to k plus 1, the right-hand side equals to k plus 1 times k plus 1 plus 1 divided by 2, perfect square. And this is exactly k plus 1, k plus 1 plus 1 divided by 2, perfect square. You see? This is exactly what I need to prove. So that being said, this is the case for, therefore, the left-hand side equals to the right-hand side, right? This is the case for P, k plus 1. So now you have proof. Step number 1 is the base case. Step number 2, whenever you suppose n equals to k, the property holds, and then you have already created, okay, all the kind of like a little calculation, and then figure out the thing works for n equals to k plus 1, right? So therefore, you finish up your step number 1 and your step number 2. With all of this, you will be able to go to your step number 3 as a conclusion that we can claim whenever n equals to all those positive integers, the property holds, right? That's actually a proof for such a problem, right? You see, this process is very understandable, right? It's a very understandable process. What you're going to do is always use n equals to k to prove n equals to k plus 1. And during the process, the most important thing is you need to utilize your hypothesis, right? That's kind of the seed, right? You need to use the seed to generate another one, and then use the new seed to generate another one, so on and so forth. So the most important thing is you need to introduce whatever you have already hypothesized and try to do this next step. So far, so good? Okay, yeah, I just want to have a quick survey for you guys. Have you guys already know this mathematical induction method? I like to see where you stand. If you're all good, then I do not have to go for something in like so much details. And if all good, we can just try to do some flowery problems. Can I have some feedbacks? So please, everyone, give me a feedback. You can use the group chat with me. Can I have some quick feedbacks? Having a good communication between us is extremely important. You can open your kind of like your chat function, communicate with me. I want to see where we stand. If we're all good, or we're kind of okay for that, so on and so forth, that's going to be basically, we will be able to adjust the speed of lecture and make sure we're all on the same page. Are we all good? Can I have some feedbacks, please? There's only one student respond to me. Okay. Yeah, sure. Yeah, I think most of the students are kind of like familiar and with this. Yes, I still gonna give you like more explanations, but just want to make sure if we're all on the same page that we do not have to go for like so much details with all those kind of like ABC stuff. Okay, no problem. We can always adjust. Like the good part of our lecture is I'm actually listening to you guys, and all the lecture's complexity will be adjusted based on our audience. If you think it's too easy, too difficult, we can always do some adjustment. Okay, so this is actually our question number 1. All right, it's considered to be a warm-up question. You understand what is the protocol whenever you want to use the mathematical induction method. So trust me, mathematical induction method is actually very important. And most of the AMC or like our Canadian math competitions is actually going to use it from time to time. Well, the good part is for our AMC exam, sometimes you do not really have to give the proof, right? As long as you can guess out the numbers, you're good to go. So you will be able to see a lot of problems from AMC. You do not really have to prove anything. But as long as you find out a pattern, you can guess out a pattern and solve the problem immediately. For Canadian math competition, sometimes you have to give some rigorous explanations. You can't just guess out, right? You have to give some rationale behind it. So actually, this proving process is more important for for the Euclid, for COMC, where you need to present all your explanations. However, in AMC, the same thing. As long as you want to guess out something, sometimes having a more rigorous proof can from time to time very help you to emphasize your problem. So let's go for one AMC problem. It's actually easy AMC problem as well. I just want to show you guys, look, this kind of mathematical induction method can be utilized all over the places. This is like an easy AMC problem. This is a problem from 2019, AMC 12A, question number 9. It's a fairly easy problem. However, I just like to show you guys, you see, even though we're easy problem, this is actually a direct application for the mathematical induction method. So this problem says, a sequence of numbers defined recursively by A1 equals to 1, A2 equals to 3 over 7, and AN. AN is actually defined recursively using such a method. AN equals to AN minus 2 times AN minus 1 over 2 AN minus 2 minus AN minus 1. So any term is actually solely determined by the first 2 terms. Okay, this actually holds for whenever n is greater or equal to 3. And then A2019 can be presented using P over Q, where P over Q are relatively prime positive integers. What's the value for P plus Q? So this is actually a typical AMC way, ask you how to present the value, right? So long story short, you need to find out what's the value for A2019. All right. So as long as you see such a problem, I think we have already introduced a lot in our math competition courses. As long as the question gives you a weird number, A2019, this is like a big number. You won't be able to calculate all the way to 2019. As long as the question gives you a sequence, give you a first couple of terms, so on and so forth, and then the question asks you to determine a weird number. So who can tell me, what is the conditional react? Normally speaking, what are the 2 possible approaches for such a problem? Please, you can post your answers into the group chat, and we will be able to have a lot of interactions. I'm going to be asking you guys to basically answer my questions. Interaction is very important. So I'll be asking for Wayne. What is the common practice for such a problem?
Find a pattern.
Is that right? Find a pattern. So that's perfect answer, right? And this pattern, normally speaking, it has two scenarios. Who can tell me, normally speaking, what these patterns might look like? Who can tell me? It might, what kind of patterns you might be expecting in such a problem? I can tell you there are two scenarios. Who can tell me? According to our experience in AMC, this pattern, normally speaking, there are only two patterns. So whenever you want to think the problem, you want to think from such a direction. There are only two patterns you can do. One pattern is you can go basically looking at a very understandable formula, right? You might end up as a formula. Let's say AN might be, I don't know, maybe 3n squared plus 1, for instance. Okay, this might be a pattern. It's a very easy formula. As long as you go with this formula, you'll be able to calculate the first one, the second one, okay, so on and so forth. Well, the second one is also very important. This pattern might be a periodic pattern. Okay, you won't be able to find a formula for an, but you can find out an would be a periodic function. So a1, a2, I don't know, maybe all the way to a7. This is actually a cycle. As long as you finish up the 7, a8 goes to a1, a9 goes to a2, right? So that being said, you need to figure out what is 2019's position within this cycle, right? So 2019 is congruent to what? Modulo this cycle, right? And you will be able to find out the corresponding value for 2019. Okay? So like I said, if you check all the AMC problems, it's either one or the other. It won't be able to give you the third one. Either it's very easy formula, you got it, you finished up, or you can see a periodic function, periodic pattern, to after a certain pattern, it repeats for itself. You just go to a certain number, then you're good to go. So far, so good. So try to bear in mind, these are the two very important patterns you're expecting for the AMC. So that being said, who can tell me? So just plug in the value. I already have a1, which is equal to 1. a2 equals to 3 over 7. You know what? I can basically plug in the value, try to do some calculation. I can a3, 3 over 11, a4, 3 over 15. So all the way comes to here. Who can tell me what kind of pattern you have already figured out? Who can tell me? You already get some pattern? I can give you this. This is a5. Who can tell me? What is the pattern? Yeah, you can use the group chat. You can talk with me. This is very important. We like to have more interactions, so on and so forth. I'll be asking for Alex. You can unmute yourself and you can answer the questions if you like.
Okay. I just said the denominator increased by 4 each time.
Is that right? That's a brilliant observation. Then you can find out an actually equals to 3 over 4n minus 1. Just plug in the number, right? Every time you increase by 1, every time you increase by 4, so that being said, it's going to be 4n something, right? This is actually your pattern, right? Actually, from AMC's perspective, as long as you find your pattern, you just plug in the value whenever n equals to 2019, right? Then you will be able to get your answer A 2019 equals to 3/8075. That's it. Do we have this? A075, you have to basically add those numbers together, and you have the E part, 8078. This is quite understandable, right? From AMC's perspective, that's the good answer. You're good to go. However, how you can prove it, right? How you can prove this is always correct. This is going to be something AMC is not really required. However, the mathematical induction method can really help you to prove, you know what? Actually, AN indeed equals to 3/4n minus 1. How you can prove it? This is actually the proving process. In order to use our mathematical induction method, so step number 1, we just basically let a value, right? N equals to, in our case, n equals to 3, right? This is actually our base case. So even though the problem, whenever we use our mathematical induction method, the definition starts from n equals to 1, but you can be more a little bit dynamic, adaptive. Sometimes this problem actually happens whenever n is greater or equal to 3, right? So you can actually find out the base condition for n equals to 3. You do not really have to jump to n equals to 1 as a start, right? And then your step number 2 is you want to suppose a k equals to, in our case, this is the, I'm going to say it here. Okay, I'm going to, oops, why I cannot erase it. Okay, anyway. So the next step is you need to do the suppose, because you guess this AK might looks like AN equals to 3/4 minus 1. So you can suppose AK equals to 3/4K minus 1, right? Using such a hypothesis, you want to show the value for AK plus 1, right? So what's the value for AK plus 1? According to the question, AK plus 1 is actually equals to this, right? I'm going to put it in. AK plus 1 will be AK minus 1 times AK 2 AK minus 1 minus AK, right? And then, like I said, the most important thing is that you want to use your hypothesis in order to help you to fix the problem, right? So now it's time to plug in the value for AK minus 1 and AK, because you just hypothesize AK equals to 3/4K minus 1, right? In that case, it's going to be 3/4K minus 1 minus 1, 3/4K minus 1. 2, 3/4K minus 1 minus 1 minus 3/4K minus 1. You just have to plug in this. And then what you have to do is you just basically do some quick analysis and you'll be able to get, this is going to be 3/4K plus 1 minus 1. And this is exactly your hypothesis whenever K equals to K plus 1, right? This is exactly your AK plus 1 equals to the right-hand side. So therefore, step number 3, this property holds for all positive integers whenever n is greater or equal to 3. You see, this is actually a very direct application using the mathematical induction method, right? You just have to basically use your hypothesis and then try to prove your new format. But as long as you're doing the proving process, always plug in your hypothesis and make sure you can use your hypothesis during the proving process. So far, so good. This is actually a very important application using the mathematical induction method. You see, this is a quite understandable problem, right? It's only question number 9, But I like to show you that this is why hypothesis using the mathematical induction method is all over the places. So in your AMC problem, you can just do a guess. As long as you guess out a pattern, you're good to go. However, if you want to give some rigorous proof for the Canadian math competition, you can't really say guess, right? You have to give the proof. And how you can give the proof? Using the mathematical induction method, 3 steps, you will be able to prove, okay, the pattern of such a sequence is indeed 3/4 minus 1. And this is actually an application using the mathematical induction method. So far, so good? You see, these are 2 very easy peasy problems. I just want to use this as a kind of like a warm-up problem, right? You see how this mathematical induction works. And then let's go to one relatively difficult problem. Because I know in North American, the kind of math competitions, you won't be able to do a lot of proof. Most of the time, especially like the American exams, you just give the answer. However, know how to show you a proof is actually something very important. So we like to give you guys like step by step, not to jump to a difficult problem right away. Let's try to do some relatively easy ones to warm up. And then it's time for us to go for one relatively difficult problem. Okay, let's go to our question number 3. We're looking at a problem from 2009 CMO camp question. So this CMO is actually the Chinese Math Olympia. Okay, we see like the winter camp question. So this is a very good problem that you can use the mathematical induction method, try to do the proof. So the problem says, let real numbers A1, A2, AN such that A1 plus A2 all the way to AN equals to 0, and A1 absolute, A2 absolute, AN absolute lesser or equal to 1. N must be a positive integer greater or equal to 2. Also, let Bn equals to An over N. N is also a positive integer. Please prove. B1 plus B2 all the way to Bn less or equal to 1 over 2, 1 over 2n. N is a positive integer. Let's have a quick look at it. How are we going to deal with such a problem? This is a relatively difficult problem. So we have real numbers, A1, A2, all the way to AN. You see, they're not integers, they're just real numbers, such that the total sum of these n numbers equal to 0. And the absolute value sum for each of the item is less or equal to 1, whenever n is greater or equal to 2 as a positive integer. Okay, this is the condition the question gives you. With all of this, the question actually defined a Bn. Bn is another sequence. What is Bn? Bn is An over N. An over N. And the question asks you to put B1 plus B2 all the way to Bn. I take an absolute value. This guy is less or equal to 1 over 2 minus 1 over 2n. Well, a problem like this. So how can you get started, right? This is kind of like, you really have no idea how to get started. However, as long as you see, you know what? You see this n. N is here. And n is all over the places. What is n? N is actually a positive integer. So as long as you see such a problem, n is a positive integer, you're kind of doing some discussion based on n, right? So this really gives you kind of like a hint. Maybe you like to do the mathematical induction method, right? Because you're looking at n as a positive integer, and n is kind of like all over the places. Maybe it's time to do a mathematical induction method. So let's have a look. how are we going to use the mathematical induction method to try to solve this? All right, in order to do the mathematical induction method, we need to go for 3 steps, right? Step number 1, find the base case. And could be 1, could be 2, could be always the base case. Step 2, hypothesize n equals to k to prove n equals to k plus 1. And step 3, let's do a quick wrap up. All right, let's just follow this 3 steps, right? I don't even know where we're going to go, but let's try to follow the 3 steps. Step 1 could be easy. Find the base case, because the question says everything starts with n equals to or greater than 2. So the base case, let n equals to 2. Let's have a quick look at it, how this one is going to work. So whenever n equals to 2, you're looking at, you have a1 plus a2 equals to 0, right? a1 absolute, a2 absolute. Their sum less or equal to 1. And with this two information, you want to prove b1 plus b2's absolute value. b1 plus b2's absolute value will be a1 plus a2 divided by 2, right? That's the definition for bn. Who can tell me how can I do such a quick proof? I have a1 plus a2 equals to 0. a1's absolute plus a2's absolute less or equal to 1. I want to prove a1 plus a2 over 2's absolute. This guy is less or equal to whatever. How can I prove this? It looks like even the base case, you need to have some quick thinking process, right? It's not just given right away. How are we going to do from these two to prove this guy? Who can tell me? Think about it. I'll give a quick hint. Maybe you need to use some absolute values basic property. You're looking at the absolute values inequality, right? Absolute value inequality. Maybe try to use some basic concepts for the absolute value. Maybe we could be able to solve the problem. Think about it. It looks like you have 2 variables. One is a1, one is a2. If you can somehow find out the relationship between these 2 variables, maybe you can solve the problem. Think about it. How are we going to deal with such a problem? Please, everyone, please get involved into the discussion process. I like everyone to get involved. Yeah, I see somebody already has the correct answer. Yeah, this is not something too complicated. You just need to do a very quick tweak, and then you're good to go. I'll be asking for Wayne. What do you think?
At first I convert b1 plus b2 into 0 minus a2 over 2 because a1 plus a2 will be 0, and a1 plus a2 over 2 will be 0 minus a2 over 2, and the absolute of that will just be a2 over 2, and then since absolute value of a1 plus the absolute value of a2 is smaller or equal to 1, and then you just divide by 2 on both sides. So therefore you get absolute value of a1 over 2 plus the absolute value of a2 over 2 will be smaller or equal to 1 over 2. And then just plug that into the the thing that you want to prove.
Is that right? That's a brilliant process. Yeah, I think that's a very nice explanation because, like I said, you only have like two numbers, A1 and A2. You won't do too much flowery works, right? Like I said, you need to find out the relationship. Now you have two variables. Maybe reduce them, right, into one variable. Maybe you're good to go. This guy, you have what? A1 equals to minus A2, right? So that being said, A1 absolute plus A2. A2 is actually minus A1. This guy is less or equal to 1. So that being said, A1 absolute is less or equal to 1 over 2. But A1 and A2, they're basically the same absolute value. It's only the sign is different. Now this guy is what? A1 is equals to minus A2. So A1 minus A1 over 2, right? That's going to be A1 over 2 absolute. Quite understandable, right? A1 over 2 absolute. A1 is less or equal to 1 over 2. So A1 over 2 will basically less or equal to 1 over 4, right? This is nothing too tricky. Very understandable process. Well, if this guy is less or equal to 1 over 4, what I need to prove? I need to prove whenever n equals to 2, right? This is base case. So the right-hand side will be 1 over 2 minus 2 times 2, which is 1 over 4. Perfect, right? You just want to prove B1 plus B2 less or equal to 1 over 4. And we just prove this guy is less or equal to 1 over 3. QED for our step number 1, right? This is only the base case. I think this is something quite understandable. Now, let's go to the most important part, our step number 2. Suppose n equals to k, the property holds. N equals to k, the property holds means what? Means whenever you have k, A1, A2, all the way to AK, their sum is equal to 0, and their absolute value sum is less or equal to 1. If you define a Bn, you can make sure this guy works, right? This is not only one condition, it's actually two prerequisites, two conditions, and then go to a conclusion, right? This part is a little bit difficult than the previous one. You have to make sure n equals to k, the property holds. It means, that is to say, A1 plus A2, AK equal to 0, A1 absolute, A2 absolute, AK absolute, less or equal to 1. With these two conditions, you want to find out B1, B2, BK less or equal to 1 over 2 minus 1 over 2k, right? This is basically what you have already consumed. You have already, what should I say, hypothesized, right? This is what you already hypothesized. And you want to prove, we want to check. Whenever n equals to k plus 1, whenever n equals to k plus 1, you're still going to have those guys adding them together equals to 1. Those guys adding them together less or equal to 1. You want to prove for now, these guys hold. Right? You need to understand what is your hypothesis, what is your conclusion. Right? So whenever n equals to k plus 1, we have A1, A2, AK plus 1 equals to 0, A1 absolute, A2 absolute, AK plus 1 absolute less or equal to 1. These are still valid as a condition. And you want to show the value for B1 B2 all the way to BK plus 1, right? You want to prove this guy is true or not? Right? This is the part you're trying to show. You want to show this, so it's still a question mark, right? All right, if that's the case, let's have a look at, can we use this number 1 and number 2 to figure out our blue question mark part? This is basically where we need to do, right? Okay, so let's have a quick analysis how this one works. We're going to use something quite similar as we did before. A1 plus A2 all the way to AK plus AK plus 1, right? Now you're telling me this guy equals to 0. So that being said, A1 plus A2 all the way to AK equals to AK plus 1 if you're talking about the absolute value, right? These two parts, you just are like a sign different. Well, the other parts is basically if you take an absolute value, they're exactly the same. So that being said, because you want to use your second condition, right? How can I do the second condition? A1 absolute, A2 absolute, all the way AK, all the way go to your AK plus 1 absolute. This guy is actually less or equal to 1, right? This is actually given by the problem. Well, this guy, I can say, this guy, I'm going to maybe drag it here. Just give me 1 sec. I'm going to drag here. Okay, good. Okay, this guy using some basic absolute value inequality, this guy is actually greater or equal to A1 plus A2, AK absolute plus AK plus 1 absolute. Is it right? Do you guys follow me on this part? So this guy, every single item's absolute value, of course, it's greater or equal to, the first couple of K terms take absolute value, and then the K plus 1 terms absolute value, which is totally understandable, right? So you are telling me that this guy and this guy, they have the same absolute value. This guy has the same absolute value. So that being said means what? 2 AK plus 1 absolute value will be lesser or equal to 1. AKA AK plus 1 absolute value is going to be less or equal to 1 over 2. Right? You see, this proving process is almost the same as what we do for the first one. Right? The previous one is only for 2 terms. Now I just generalize it into K plus 1 terms. But the thinking process is fairly understandable because you need to find, because as long as you go to n equals to K plus 1, this is the newly added term, AK plus 1 absolute. Of course, you need to find out what this guy looks like. What is the relationship for this guy? Right? All right, so intuitively, as long as you got a value for AK plus 1, so what can I do? Let us validate your left-hand side, which is B1 plus B2 all the way to BK plus 1, right? Absolute value. Let's have a quick look at it. You are telling me because this guy, according to the definition, is less or equal to B1 plus B2 all the way to BK plus BK plus 1, right? This is exactly the same thing as we did for the, for the AK plus 1 term. So, because like I keep saying, you always need to use your hypothesis. Now it's time to use our hypothesis, right? This is your hypothesis. Your hypothesis is, as long as n equals to K, you have B1 all the way plus BK absolute value less or equal to 1 over 2 minus 1 over 2K. This is a very perfect place for you to plug in this value, right? Less or equal to 1 over 2 minus 1 over 2K. And what about this? BK. BK plus 1. BK plus 1 just equals to AK plus 1 over K plus 1, right? Why? Because your BK is here. BK is defined as AN. BK is actually defined as AK over K, right? You see, everything is like so harmonic, right? It's time plug in this. This guy equals to this. Because you just figure out AK plus 1 absolute value is less or equal to 1 or 2. So this guy will be less or equal to 2. K plus 1. So harmonic, right? So adding them together, this guy will be less or equal to 1 over 2 plus 1 over K plus 1 minus 1 over K. Do you guys follow me? Can I have some feedbacks? Are you guys following me? Yes or no? Which is quite understandable, right? There's nothing to flourish. That's it. But normally speaking, I should wrap it up. You see, I finished my work. Let's try to see the right-hand side, and then my work is done. Well, the problem is, as long as you see the right-hand side, the right-hand side is what? Here, the right-hand side should be whenever n equals to k plus 1, the right-hand side is 1 over 2 minus 1 over 2k plus 1. 1 over 2 plus or minus. So let me see. Plus or minus. Minus. All the way I comes to here. Oh my God. There is a problem. The left-hand side is actually this. Well, the right-hand side is this. This is not exactly what I want, right? This is not exactly what I want. Well, if you really want to have this 1 over, see, if you really want to have this 1 over 2k plus 1, you see, the right-hand side is negative. The left-hand side is positive, but that part, no problem, because you can always change this into negative. Oh, no, you can't change it to negative. I'm sorry, you can't, yeah. So that being said, there's a difference. Yeah, the left-hand side is actually, you have 1 over 2. You have 1 over 2k plus 1. It's kind of similar, but you have this weird term. A term which is not tolerable. 1 over 2k. The right-hand side do not even have this 1 over 2k. How can I solve this problem, right? The left-hand side and left-hand side, the right-hand side and left-hand, they're not the same. They have to be exactly the same to make sure you can wrap up your conclusion. But now they're not the same. You won't be able to prove this guy is always less or equal to this guy. You just can't. So that is actually a big problem that we have to solve. As long as you solve this problem, you might be able to move forward. Otherwise, you just can't. Well, this is actually the most challenging part of this problem, because you can't use a very linear thinking process. All the way come to here, it's a very linear thinking process. Well, the difficult, because as this is like a CMO winter camp question, you need to do some flowery things. So it looks like the black sheep of the family is actually this 1 over 2k, right? I need to properly handle this 1 over 2k, right? As long as I can properly handle this 1 over 2k, I might be able to cancel, right, this 1 over 2k, and even change the factor, change the sign of this 1 over 2k plus 1, and then eventually help me solve the problem. But the $1 million question is, how can I get rid of this 1 over 2k? In order to get rid of this 1 over 2k, think about it. We just did something like this. K plus 1, AK plus 1 absolute value is less or equal to 1 over 2. How can I use such a condition to make sure I can properly handle this 1 over 2k? This is actually the most challenging part of this problem, because I need to construct a 1 over 2k. And I need to use something, I can't just put a 1 over 2k, right? And I need to use something what I just created in order to facilitate this 1 over 2k. And the solution for such a problem is actually, let's try to create a ak plus 1 over k term. This is the construction. Construction means you have to create something from nothing, right? I need to create such a term, aka, I want to have the 1 over 2k. What is the most cost-effective way? Since I have already figured out ak plus 1's absolute value is actually less than 1 over 2, let's do a k, then you will be able to make it work. Quite understandable process, right? This is actually the thinking process. How do you think about you want to do this? There's a rational. The rational is you're kind of offset by 1 over 2k. What is the most cost-effective way? You just figure out ak plus 1 is less than or equal to 1 over 2. Just let it over k. Then you will be able to solve the problem. So what you need to do is, I'm still gonna do the left-hand side, right? Equals to b1 plus b2 all the way to bk plus 1, right? So now b1 is actually what? b1, b2, all the way to bk. bk is actually ak over k, right? bk plus 1 is ak plus 1 over k plus 1. How can I just insert this kind of like ak plus 1 over k plus 1? The most effective way is I'm going to add ak plus 1 over k and minus ak plus 1 over k. Is that right? Because like I said, ak plus 1 is less or equal to 1 over 2. So divided by k, that's going to be able to help you to create this 1 over 2k. This is actually the beautiful part of such a problem. And I need to calculate what is the range for such a guy. So this guy, I can do a quick analysis, b1 plus b2 all the way to bk minus 1. You see, what I will be doing is that I'm going to use this k here. Okay, I'm going to using this k here. ak plus 1 over k and plus ak plus 1, k plus 1 minus ak plus 1, k. Okay, I didn't do anything. I just basically swapped the order for these two guys. Now, what I need to do is this guy should be lesser or equal to b1, b2, all the way to bk minus 1, ak plus 1k. And this is going to be 1 plus 1 minus k, ak plus 1. Is that right? Do you guys follow me? I didn't do anything too complicated. I just basically swap the order of all these terms. And then I basically, you see, these guys, I make one absolute value. These two guys, I make the second absolute value. So far, so good? You guys follow me? Now, you need some algebra calculation together, but generally speaking, there's nothing too complicated. Are we all good? Can I have some feedbacks? Are we all good? Are we all good? Or you get confused at certain part? Okay, perfect. Yeah. Now, I didn't really use my hypothesis yet, right? So I need to figure out how I can use my hypothesis. Do you still remember my hypothesis? My hypothesis is actually way up here. This is my hypothesis. I'm going to basically rewrite my hypothesis one more time, right? My hypothesis is whenever n equals to k, a1 plus a2 all the way to ak equals to 0, A1 absolute value, A2 absolute value, AK absolute value less or equal to 1, right? As long as I have these two things, I would be able to say B1 plus B2 all the way to BK absolute value less or equal to 1 over 2 minus 1 over 2K. Okay. I think most of the students will say, hey, Alex, you can't use your hypothesis because your hypothesis says this is going to be AK. You're going to stop your work at AK, right? And then you'll do a BK. But for now, this is no longer AK. This is like AK plus 1. I mean, this is AK plus 1 divided by K, right? This is not your hypothesis. I can't really use my hypothesis, right? Do you guys follow me? Right? Because previously it was like all the way go to like AK, but now it goes to AK plus 1 divided by K. This is not AK. How can I use my hypothesis? Does it make sense? You guys follow me? Yeah, this problem is a little bit challenging. We're going to make sure we're all on the same page. So I won't be blaming you because they're not the same thing. However, the challenging part of this problem is here, we're going to do such an analysis. Yes, I totally understand these are not the same thing, right? No problem. However, A1, A2, all the way to AK, it can be everything, can be anything, right? The question doesn't say A1 equals to 1 or 2 or something, or A2 equals to something, something. All the way to AK, it can be whatever, whatever. If that's the thing, maybe I can put AK into something different. So I'm going to keep the A1, A2 all the way to AK minus 1. They're all perfect things. But AK, I'm going to let this AK equal to a bigger AK. And this guy equals to AK plus 1. Is it going to work? Because AK is actually a box, right? You can put whatever value in it. This time, I'm going to put a specific value. This value is actually AK plus 1. So if that's the case, this guy is going to be what? AK plus 1. Is that right? So that being said, because AK is actually, I can put whatever things I want to put. Does not necessarily needs to be AK. It could be AK plus 1. If that's the case, in my current BK will be my AK over K. In that case, will be AK plus 1 over K. Is it right? If that's the case, it actually means what? I can still use my hypothesis. But this time, the hypothesis, the only difference is that this is actually my new AK. I'll keep all the values from A1 to AK minus 1 exactly the same way, but I'm going to switch. I'm going to convert my AK, my lowercase AK, into my uppercase AK. And my uppercase AK is exactly AK plus 1. And if that's the case, I can still use my hypothesis. Do you guys follow me? This is the most challenging part of such a problem. We have to do a construction, no problem, but this is the most challenging part. A lot of students cannot do such a replacement. We'll actually generalize the value for AK. AK is a box. You can put AK, lowercase AK in, but you can also put lowercase AK plus lowercase AK plus 1 in. It doesn't change anything because this is only a symbol, it's only a denotation. It does not change the value at all for our entire process. Do you guys follow me? This is the most challenging part of such a problem. Okay? As long as you understand this part, that being said, here, I can still use my hypothesis. Even though it does not look like the original hypothesis, but you can still use my hypothesis. Because in my hypothesis, my AK has been replaced by using uppercase AK, which is AK plus AK plus 1. And my BK has already been replaced using my uppercase AK over K, which is AK plus AK plus 1 divided by K. So this is going to be AK. This is the very, what should I say, abnormal way to solve the problem. That's the beauty of our CMO, like winter camp, right? It is basically to change this, but you still would be able to use your AK plus 1 divided by K to figure out this guy as actually less or equal to 1 over 2 minus 1 over 2K. So that part will be less or equal to 1 over 2, 1 over 2K. Plus, this part, I'm just going to plug it in, right? There's nothing special. Because AK plus 1 is less or equal to 1 over 2, right? This is, we already calculated. So these two parts will be less or equal to K plus 1, 1 over 2. So that being said, your entire expression will be less or equal to 1 over 2, 1 over 2K, 1 over 2. If you do the calculation, that one will be exactly equals to 2K plus 1, which is exactly the right-hand side. So now you successfully prove whenever n equals to K, it holds, and then you prove n equals to K plus 1, it holds. This is exactly the K plus 1 case. So now you prove the base case, you prove the second step, and step number 3. So this entire property is going to hold for all the integers greater or equal to 2, QET. See, this problem is a little bit challenging, right? It's not like the easy peasy problem. It basically utilized many important concepts in order to make it work. Let's have a very quick recap, right? Let's have a very quick recap. So the most complicated part is whenever n equals to K, you want to prove that n equals to K plus 1. If you follow our standard way, nothing special, you just basically use our conditional intuition, right? You put all the previous parts together, you put it here, right? All the way to here, you're going to find something like this. This is exactly not what we want. Something quite similar, but you have this 1 over 2K term, which is totally beyond us. How can I get rid of this 1 over 2K? The most important thing is you figure out the value for AK plus 1. The absolute value for AK plus 1 is less or equal to 1 over 2. So using AK plus 1 over K is the most straightforward way in order to construct 1 over 2K, right? But how can you do that? This is actually a very standard way in the math competition. Add a term and remove a term, right? You're going to see this is a very typical construction way. Add a term, remove term. Okay, as long as you add a term, you remove term, it's quite understandable. You put all those, BK-like terms together, all those AK plus 1-like terms together, which is totally no problem. But the challenge is that at the very beginning, you might get confused. How can I use my hypothesis? Because my hypothesis, the last term is AK, but your last term is kind of like AK plus 1. I just can't use it, right? However, a quick analysis told you that this AK is only like a house, right? This is kind of like a black box. You can put whatever value. You can put AK. You can even put AK plus 1. As long as you put this AK plus 1 inside, you will be able to generate a new AK. We'll say the uppercase AK, right? But it doesn't change anything. It's just a denotation. That's it. Now you will be able to say this is actually a uppercase AK over K reaches the definition of BK. You can use your hypothesis right away, right? It's not a direct way, but you can just do a quick tweak to make it still talking about the same thing. As long as you have this, I think the following part would be very easy. You can directly use your hypothesis, right? Because B1 plus all the way to BK will be less or equal to 1 over K, 1 over 2 minus 1 over 2K. And taking from there, the latter part, you can just use the property for the AK plus 1, which is less or equal to 1 over K. You can find out such a relationship. Adding them together, you have the problem solved right away. This problem is very challenging. It's much difficult than our first two problems, but still give you an idea that whenever you use this mathematical induction method, this AK can be very adaptive. Not always the very, very old one, right? But you can use some adaptation to make it work. And this is where we come from for our problem number 3. Do you guys following me? Can I have some feedbacks? I'm sorry, I think we're extra silent today. Do we have any feedbacks? Are we good? Yes or no? Can I have some feedbacks? Are we all good? If you don't understand, you can let me know. Don't be quiet. If you're silent all the time, I can't really read your mind, so I don't know. Can I have some? Are we all good? Okay. Perfect. The other students? Okay, perfect. If you're all good. So this is actually a little bit challenging, not very direct how to solve the problem. We can use the problem. We can solve the problem in such a way. So these are basically the problem that, we have like 3 problems. It's pretty much this algebra problem. Try to use the mathematical induction method to solve it. You know what? Actually, mathematical induction method can help us to solve some geometry problem as well. So let's go for some geometry problems. Let's have a look at it. How are we going to use the mathematical induction to solve some kind of like weird, if not impossible, geometry problem? Okay. This is our question number 4, right? Let's say there is a 2 times 2 to the power of n times 2 to the power of n square matrix. Please prove. Okay, nothing, just one condition. 2 to the power of n times 2 to the power of n square matrix. I have so many little squares. Let's prove. If one square is removed from this matrix, the remaining part can be fully covered using such an L-shape pattern without any overlap. Okay, that's the problem. The problem says, let's say I have a square matrix. So basically, I might have something like this, right? They're all squares. They are 2 to the power of n times 2 to the power of n, right? 2 to the power of n times 2 to the power of n. They're like a matrix. So this matrix have like so many squares, right? 2 to the power of n times 2 to the power of n squares. If one square is removed randomly, you remove one square from this matrix. The remaining part can be fully covered by using such a L shape. So there's 3 squares using the L shape without any overlap. Oh my God, how can I solve such a problem, right? I totally have no idea how the thing looks like, right? I can't really use like little things to do this kind of like enumeration. This is impossible. There's this problem, there's no way to solve it using the traditional. There's no way to solve it using a direct method, right? Because you don't even know where to move it. So this way, this is actually a very famous problem that you need to use the mathematical induction method to prove it. Because mathematical induction method, the good part is whenever you do step number 2, suppose n equals to k, the property holds, right? In this part, you do not have to give any proof. You're all good. You just suppose it is work. That's it. You just have to prove whenever n equals to k, it holds. Whenever n equals to k plus 1, it holds as well. That's it. So let's try to see how you're going to deal with such a problem, right? Like I said, direct way, no way to do it. Let's use the mathematical induction way. So step number 1, base case. Base case, whenever n equals to 1, whenever n equals to 1, you're looking at a 2 times 2 square, right? 2 times 2 square. If you remove one little square, of course, the remaining one would be covered using this using this L shape, right? Obviously, valid. Or like the property holds. This is nothing to say, right? Then step number 2, suppose n equals to k, the property holds, means I have this 2 to the power of n, 2 to the power of n. I randomly remove one in the middle, right? Or like whatever, right? The remaining pattern will be fully covered by this little L shape with no overlap, right? The most important thing is, let's check n equals to k plus 1. So first thing first for you guys, what's the relationship for this n equals to k shape at n equals to k plus 1 shape? Who can tell me? Who can tell me? N equals to k, n equals to k plus 1. You need to find out the relationship before you can do anything, right? This is very conspicuous. Who can tell me? What's the relationship between this n plus 1 and n plus k plus 1? N equals to k, n equals to k plus 1. Is there any relationship between the two? I'll ask for Kayla.
The area of the n equals k plus 1 shape is 4 times the area of the n equals k shape.
Is that right? This is quite understandable, right? So let's say I'm going to have this. Now it is going to be n plus k plus 1. I'm going to put it here. So that being said, if I put it here, so this is going to be a 2 to the power of n, 2 to the power of n, right? So this is actually 4 times quadrilant of our n equals to k, right? I'm sorry, this is k, right? Not n, k. Okay. You see, now I'm going to remove one part from this big shape, right? 1 cubit. So if I just want to remove 1 cubit, so it could be basically go to one of these 4 quadrilant, right? One of these 4 quadrilant. Okay, without the loss of generality, maybe I'm going to remove it from here. Without the loss of generality, the square is removed from quadrant 3. Okay? Because you know this is like 4 times. Okay, my goal is try to use our hypothesis, right? I have to use my hypothesis. My hypothesis says as long as you have a 2 to the power of k times 2 to the power of k term, you have such a cube, you have such a metric, remove one, fully recovered by my L shape. So that being said, my quadrant number 3, no problem. This guy will be fully covered by the L shape. Is that right? Quadrant number 3 will be fully covered by L shape. This is actually using our hypothesis, right? Or suppose. But I still have 3. I still have 3 2k times 2k ones, and nothing is removed from there. How can I deal with that? Right? You still have like 3 other shapes. Those, I'm okay for the third one, right? You remove one cubic, everything is fine, fully covered by the L shape. But what about the other 3? The other 3, there's nothing I removed, right? If I didn't remove anything, of course, I can't really use my hypothesis to make sure it is going to be fully covered by the L shape. Is there any way for me to use the hypothesis for the other 3 shapes? As long, because my goal is I need to use my hypothesis. I want to say this entire big shape is going to be covered by the little L shape, right? But now the other 3 squares, quadrant 1, 2, and 4, there's not even like a single cubic is removed from the part. How can I actively create something to make sure I can still remove from that? Who can tell me? Again, you're creating something which is not there originally, right? Maybe you have to do some construction. Construction is you need to remove 1 square from the other 3 shapes. Okay. How can you remove it? Of course, whenever you remove one, let's say if I remove one from here, for instance, so this guy is going to be definitely fully covered by the L shape, right? If I remove one from here, fully covered. If I remove one from here, fully covered. But what about like the removing ones, right? I'll be asking for Alex.
Oh, okay. So I'm just thinking that you could like remove the one that is closest to the origin so that you can like apply the L shape right away.
Is that right? That's a brilliant observation. I'm going to remove one from the 3 black part, for the 3 blank parts. But as long as I remove one, I'm not randomly remove one, because as long as you remove one, it works, right? My hypothesis says as long as you remove one, it is good. But the one I remove, I want to make it a little bit smart. I want to remove the 3 squares, which is adjacent, which is very close to this orange. So as long as I remove one, all the remaining parts, 1, 2, 3, they will be fully covered using your hypothesis. And also, my 3 removed 1 little squares will be already create an L shape, right? So of course, my green parts will be covered by the L shape, while the remaining 3 blank ones will also be covered using your hypothesis. So that being said, your new shape will definitely be covered using your hypothesis. So far, so good. So a quick word with that is that you remove 3 blocks from the 3 blank squares and make sure it's actually close to the orange. Okay? You can use the hypothesis on the 3 blank squares plus the little L shape around the orange. So therefore, they will be fully covered by L shapes. QED. You see? This is actually a very interesting problem. And like I said, there's no way for you to solve the problem without using mathematical induction method, right? So this is like you can see, you actually need a little bit of construction, how to place this 3 little blocks, right? As long as you place them smartly, you will be able to solve the problem. Are we all good? So far, so good for such a problem? Can I have some feedbacks? You see, it's very understandable, right? If all good, let's go for another problem. Also like a geometry problem using the mathematical induction method. This is our question number 5. Given 3 times n factorial points on the plane, any 3 of them are not collinear. Okay, any 3 of the 3 times n factorial points are collinear. Connecting them using segments. Okay, all the points connected them using segments. Color the segments. Color each segment using one color. In total, there are no more than n colors. Proof. There must be 3 points. All the segments between them are of the same color. Okay. This is also a very nice problem using mathematical induction method. I have 3 times n factorial points on the plane, many points. And none of them, and any 3 of them are not collinear. Okay, you won't have like 3 points collinear. Okay, connecting all those points. So I'm gonna have all those points, right? Random points, whatever. Connecting all those points, any 2 of them using segments. So there will be so many segments, right? Color each segment using one color. This is black. Maybe this is blue. Maybe this is green, like a red. Maybe this is green, whatever. Okay. But in total, there are no more than n colors. You have 3 times n factorial points, but you only have n colors. Okay. You do not have too many colors. Proof. There must be 3 points. All the segments between them are actually using the same color. It means that as long as you're done for everything, there must be 3 points. You're connecting them using the same color. So this triangle must have the same color for all the segments. Again, this problem, you're using the regular way to solve it. There's no way to solve it, right? You don't even know how those points looks like, how they are arranged, right? Again, these problem using the traditional way, there's no way to solve it. We have to use the mathematical induction way to solve it. Because whenever you do the step number 2, you do not have to give the proof. You just suppose it works, hypothesize it works, and then do the following part. It's actually easier, right? Otherwise, all the other proving strategies, every single step, you need to give a rational, right? So for now, how can you prove this? Even for n equals to k, there's no way for you to prove it. You can just maybe on top of your head, suppose it is correct. I'm going to prove n equals to k plus 1. So it's kind of easier for you to do the first part. All your problems just go to the second part. You don't have to prove n equals to k, it works. You just have to prove whenever n equals to k, it works. It also works n equals to k plus 1. You kind of transfer the problem. You do not have to prove the original one. You just prove this iteration part. That's it. Okay, so let's get started. We start from the easy one, right? Step number 1. N equals to 1. N equals to 1, you have 3 times 1 factorial, 3 points. And how many color? N equals to 1. 3 points, 1 color. Of course, you're going to have a triangle with the 3 sides the same color. That properly holds. Step 2, suppose n equals to k. It works. It means what? Whenever you have 3 times k factorial points, whenever you have n equals to k color, you can find this kind of triangle, right? Basically, the 3 points having the same color. Let's try to focus. Let's check. N equals to k plus 1. Whenever n equals to k plus 1, you have 3 times k plus 1 factorial points, right? Okay. Whenever you have the 3 times k plus 1 factorial points, let's try to find a point for a given point. From this point, how many segments you can eliminate, right? You can eliminate. How many segments you can eliminate? I have 3 times k plus 1 factorial points. If I take one, because I have to make the connection with all of the points, all of the other points. So how many segments it actually raise from this specific point? Who can tell me? I have 3 times k plus 1 factorial points. From all those, every 2 points, there's a connection. Every 2 points. If I just take 1 point, how many segments ray from this point, emanates from this point? Three k plus 1 factorial, choose 2? No. But what about the other? Wait, what's the, how many points? How many segments?
Just a total point minus 1.
Is it right? That one is easy. You have 5 points. Every point need to connect to each other. If you pick up 1, you have to connect 4, right? So there are these many segments emanate from it. This is understandable, right? You just basically have to connect with everyone. And how many color I have? K plus 1 color, right? Because n equals to k color. N equals to k plus 1 color. From this A point, I can ray out 3k plus 1 factorial minus 1 segment. However, I only have k plus 1 color. So that being said, among those 3 k plus 1 factorial minus 1 colors, how many of them are of the same color? Do you know this? I'm going to use different color. I have N people. Okay, I want to go to N rooms. Of course, M is greater than N. If that's the case, how many people must be in the same room? This is the pigeonhole theorem, right? Pigeonhole theorem. I have N pigeons, but there's only N holes. M is greater than N, then how many people, at least how many pigeons are in the same hole? This is M over N. Take a Gauss function plus 1. Is it right? Do you guys know this? Pigeonhole theorem. Do you guys know this? Yes or no? Pigeonhole theorem. If you have, right, if you have 3 apples, you only have 2 drawers. You put like, of course, at least there will be 1 drawer has at least 2 apples. You can have all of them be to the same apple. Like you have all of like the apple go to the same drawer. I don't really care, but at least there's a 1 drawer has 2 apples. And how can you do the calculation? You use M over N, take an integer plus 1. This is a pigeonhole, right? It's not something too complicated, right? We should, because whenever you are counting probabilities, pigeonhole is a very important theorem you have to know. Okay, so that being said, now I have 3k plus 1 factorial minus 1 segments, but I only have k plus 1 color. So therefore, using pigeonhole, there must be at least 3k plus 1 factorial minus 1 plus k plus 1 factorial plus 1 segment are of the same color. Right? This guy, if you do a quick analysis, this guy actually equals to 3k factorial. This guy actually means 3 factorial. Okay, so there are 3k factorial segments. They have the same color. 3k factorial segments, they have the same color. Okay, so I think the following part will be very easy. Let's say I have 8 points here. 1, 2, 3, 4, right? I have 3k factorial points, 3 factorial segments. They have the same color. So that being said actually means what? Okay, so let's say there are 3k factorial different points. It's actually, right? There are 3k factorial points actually flying there, right? They have the same segments actually connecting them. So in that case, let's say I have a case number 1. Let's say within this 3k factorial, within all those points, there are 3k factorial points, right? 3k factorial points. In this 3k factorial points, if 2 of them are connected using the same color of this 3k factorial segment, let's say It is quite possible, right? I really have 2 points. One is B, one is C. They happen to be connected using the same color as this three factorial segments. It is quite possible. Therefore, triangle ABC is what you want, right? Because my 3K factorial segments, they have the same color. Let's say all black. They are actually connecting to 3K factorial points. If I find 2 points from those 3K factorial points, they were connected using the same color of my black color. So therefore, this ABC is going to be what you need. You can find 3 points, create a segment, and all of them having the same color. So QED, right? You proved whenever K equals to N equals to K plus 1, it works. Or there's no guarantee, right? And what about every single points? None of them are connected using our black color. No problem. If none of them are connected using the same color of this 3 factorial segments, no problem. But there are how many points? 3K factorial points. 3K factorial points, that's going to be what? That's going to be our hypothesis, right? Those 3K factorial points must at least have 3 points having the same color. Using our hypothesis, there must be a triangle. I don't even know the triangle. They're not ABC for sure, right? They're triangle XYZ, whatever, XYZ. They are connected by using the same color. Also, QED. See? Right? For those 3 factorial points, if they have 2 already connected using the same color, you do a connection ABC, good to go. Otherwise, for those 3 points, for those 3K factorial points, okay, they should be using the hypothesis we did for our step number 2. Also, you should have a triangle. I don't know, they're not ABC, maybe XYZ, whatever. So they're also good. So in total, step number 3, it works for N equals to K plus 1, right? As long as you have the N equals to K plus 1, you should have 3 points. They are actually connected using the same color. So, QED. Voila, c'est fini. You see, using the mathematical induction method, you do not have to write a lot of formulas, calculations. It's more like some human language related analysis. Trust me, these are all difficult problems. Okay, these are more like the relatively difficult level problem, right? Because you do not really focus on the calculation, you focus on this analysis process. So this is actually what we want to say for today's lecture. You see, using the mathematical induction method, you can do a lot of algebra calculation, algebra proving, or you can do some geometry proving. But the geometry proving, you do not have to use any shape or anything. It's more like using your human language. This human language is going to be able to help you prove this. These are all very good examples of the high-level math competition. Our first lecture might be a little bit more theoretic. We didn't really get started with the arithmetic sequence, geometric sequence. These are no problem. We can do a lot of AMC, AIME problems thereafter. But I think doing this kind of mathematical induction method is kind of like a very important, kind of like it's a proving strategy to really scratch you guys from the regular calculation, process. Try to do some deep thinking in the proving, which you might not have a lot of exposure in our regular courses. We really like to take this opportunity to give you guys more interesting, flowery ways to do this proving strategy. Even in the future, we're talking about the infinite descent methodology. It's also another way how to do this proving, which might not be used quite often in our previous math competition courses, but this is going to be very important for the high-level math competition. So bear with us. We're going to give you more interesting problems to see the proving strategies before we go to the traditional arithmetic, geometric. I'm going to give you a bunch of AIME Euclid problem thereafter, but let's try to focus on this for a sec. All right, that's pretty much for our lecture number 1. And it might be a little bit unfamiliar for some of the students, but let's try to, get familiar with this kind of methodologies. All right, that's pretty much what I want to say for today's lecture. You have any questions for me? We all good? Perfect. In that case, I wish you guys a good weekend, and we'll touch base for the next week. Okay, I'm going to upload the assignment to our Google Classroom, and we can take it from there. All right, bye, guys. Have a good one.